Okay, so this section is going to go over nonlinear elements. So for the most part, we're going to focus on linear springs and dampers. However, it is possible to have nonlinear elements too. So for this figure, for a spring, a linear spring, if we were to plot our deformation or deflection versus our force, or restoring force for our spring, uh, our linear spring would just be a straight line going through the origin because all that K does is just change the slope of this. That is what a linear spring looks like. However, a nonlinear spring may look something like this or look something like this. Those are two different examples for nonlinear springs. So you can often write this as, instead of using Hooke's basic law where we just have K times D, we now have our restoring force F is equal to K, which is a function of D or deflection, times our deflection itself. And this doesn't necessarily need to be a function of deflection or deformation. It can be a function of other things too. So dampers can also be nonlinear. So F is equal to C times V, that's our linear case. F is equal to C, which is a function of V, times V. That's another case. And these nonlinearities, they can show up in the equations of motion. So for example, if we have D dot is equal to V and mv dot is equal to F minus K times, which is a function of D times D, minus C, which is a function of V times V, that is a legitimate system with a nonlinear spring and a nonlinear damper. And that nonlinear spring could even be potentially a function of deflection and velocity, as shown in the later equation. Or that spring could be or the damper could be a function of some other unknown input or parameter theta. There are many possibilities for what nonlinear elements can look like. And that's going to cover nonlinear